Welcome to Chapter 13, an introduction to derivatives. We're going to identify what a derivative is today and also be able to find derivative of functions by definition. So the first thing is, what is a derivative? First thing is, we look for slopes of lines all the time, but we can only find the slope of a line given 2 points. So a tangent line is a line that best approximates the slope at a single point. Okay, well, we know if that's the case, if we only have a single point, we can't find the slope of the line given that information. So what we're going to look at first is a secant line. A secant line intersects the graph at 2 points. So I'm going to change this line to be a secant line instead. And so now, given those 2 points, we can find the slope of the line. So how's this going to work? Well, we have to do this all in kind of general form, so it works all the time. So the point on the bottom I'm going to identify as x being the input value, and then the output value will be f of x. So wherever you plug in x, your output would be f of x. So that represents that point on the graph. And then the other point up here, well, what's the distance to that other point? We'll call it h. So then this point over here represents x plus h, because you started with the value of x and now we've added h to that. And then the output is, well, whatever the input was, which was x plus h, so it'll be f of x plus h. So that's your second point. So given these 2 points, we could always find the slope of that line. So the slope of the secant line is equal to, well, the slope is the change of y to the change of x. So the change of y would be f of x plus h, so I'm taking the top point's y value and I'm subtracting the one on the bottom, which would just be f of x. So that's the change of y over the change of x. Well, your x values are x plus h and x, and we also know the distance between the two is h because that's what we identified it as. So divided by h. So there's your slope of your secant line. But we know that. We can find the slope given 2 points. So how does this get back to the tangent line? Well, once again, the slope of the secant line between 2 points we just found as, once again, f of x plus h minus f of x divided by that change in x, which was h. So what happens here? Well, let's take this secant line and let's actually make that h value a little bit smaller. So now the distance from here to here is a little bit smaller than it was originally when it was a little bit farther out this way. Okay, so let's make it even smaller. Alright, now that h value is even smaller. Now it's over here. Okay, and let's just keep doing this until what happens? Until it becomes the tangent line. As h approaches 0, we approach this tangent line. So hopefully that leads you into what the slope of the tangent line is. Well, the slope of the tangent line is going to be equal to the limit as h approaches 0 of the slope of the secant line. Alright, so as that h value gets closer and closer and closer, what do we have? Well, we have the slope of the tangent line is equal to the limit as h approaches 0 of the slope of the secant line, which is f of x plus h, minus f of x all over h. And this right here is what a derivative is. The derivative is the slope of a tangent line at a single point. And this is how we're going to find it, by using limits. So when we spent last unit talking about limits, it's because the next thing that we're going into is derivatives, and we need to be able to find the limit of functions. And so, kind of to take everything together here, this is what we just found out. The derivative of f at x is given by, and you can see the limit as h approaches 0 of f of x plus h minus f of x over h is written, this right here, is read f prime of x, which represents the derivative. And so when we say, when we find in the derivative, we're looking for the limit there. We're answering that whole question. Okay? And so now what we're going to do is just take this opportunity to kind of go through a couple of examples of derivatives and be able to find them by definition. So we'll start first with this function. What type of function is this? This is linear. Alright, so we're going to find the derivative of this function. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. And remember, when we find limits, one of the first things we do is do direct substitution. But what happens when you plug in 0 for h? Look what you get. You get f of x minus f of x over 0, which is 0 over 0. So direct substitution doesn't work. It won't ever work for that definition of a derivative. So we're always going to have to go through that process to be able to figure it out. So what do we have? We have the limit as h approaches 0 of f of x plus h. Now, one of the things that I want to kind of go back to this slide and talk about real quick, as I kind of forgot, is when you find or given a function, let's do f of x equals x squared plus 2x. And I ask you to find, let's say, f of 3. Well, you know just to plug in 3 squared plus 2 times 3. Wherever there's x, you replace it with 3. If I say, alright, we'll find f of a. Well, wherever there's an x, you replace it with a. But then, I want you to find f of x plus h, and all of a sudden it's like, wait a second, what am I supposed to do here? Same thing, wherever there's an x, you replace it with that value. So you can see the 3, that x, and that x gets replaced with the 3. That x and that x got replaced with the a. That x and that x should get replaced with the x plus h. So instead of x being squared, now it's x plus h being squared, plus 2 times x plus h. And so that's what's going to happen on this derivative when you have to find f of x plus h. That's what you're going to be doing, is plugging in that x plus h every time there's an x. So going back to the linear function, when it says f of x plus h, we're going to go up to this function, we're going to find that x value, and we're going to replace it with x plus h. So there's the x, let's replace it with x plus h. So it'll be 4 times x plus h minus 1. So just to make sure, this right here is the same thing as that. Alright, minus f of x. Well, what's f of x? F of x is the whole thing. And since it's a quantity, we need to make sure we have it in parentheses. And so this is the same thing as this. F of x is 4x minus 1. Alright, all over h. And now we continue to simplify. Continue to write the limit as h approaches 0, because we haven't answered that question yet. So we distribute 4x plus 4h minus 1 minus 4x plus 1 all over h. Now when we did this before, the same thing's going to happen is we're looking for something to cancel. Well, we notice that the 4x is canceled. We notice that the negative 1 and positive 1 cancel. So we're left with the limit as h approaches 0 of 4h over h. We still need something to cancel. Direct substitution is not going to work. So what do we find out? The h is canceled. And so now we're left with the limit as h approaches 0 of 4. Well, what's the limit as h approaches 0 of 4? Well, 4 is just a horizontal line. So as h gets closer and closer to 0, right, from the left and from the right, it's approaching that same value of 4. So the derivative of the function is the limit as h approaches 0 of 4 is equal to 4. And we'll talk more about what that means, but we know it has to do with the slope of a tangent line. So now take the second example, which is also linear, and pause the video and go ahead and try this one on your own. It's very similar to the one I just showed you. So take that example from example 1, go through that same process, and do example 2. So the derivative is equal to the limit as h approaches 0, and I'm going to write this down every single time, and you should be doing the same thing. Let's not skip steps since we're just learning what a derivative is. The limit as h approaches 0, and this will help you remember what that definition is: f of x plus h minus f of x all over h every single time. And then you can go ahead and do your plugging things in f of x plus h. So the limit as h approaches 0, 1 minus 3 times x plus h. Once again, this right here and this are equivalent, minus f of x, whoops, which is 1 minus 3x all over h. So now simplify. That the limit as h approaches 0 of 1 minus 3x minus 3h minus 1 plus 3x all over h, and then once again look for what things are going to cancel. The negative 3x, the positive 3x, the 1, the negative 1. And now we have the limit as h approaches 0 of negative 3h over h, and then one more time, now you see the h's cancel. And so you can see that we're left with something very similar as we were the first time. The limit as h approaches 0 of negative 3 is equal to negative 3, so the derivative of the function is negative 3. And that's how you find the derivative of a linear function. Now, if you're curious, what happens if instead of using just a linear function over and over again, what if we say f of x is equal to mx plus b, and you use the general term of a linear function and apply it to the definition of a derivative, and you go through that process? What might you find out? Because one of the things that you're going to see as we're doing these definitions of certain functions is you might see patterns and you might see things get repeated and stuff like that, and you might actually realize, hey, is there a shortcut to doing a linear function? Well, if you do it by definition of the general one, you might actually find out what that shortcut is. But I'll leave that up to you guys until we kind of get to that point later on. Let's do our next function, a quadratic. Now, does anything change because we're doing a quadratic instead of a linear? No, the definition doesn't change in terms of the slope of that tangent line, so we're still going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. And here we go. So the limit as h approaches 0, wherever there's an x, you're going to plug in x plus h. Well, this is just x squared. This is just the parent function. So we'll have x plus h squared. So that's the first part. And then minus f of x, which is just x squared. So this represents that, because you're just squaring it. And then minus f of x is just your x squared. Alright, so this is equal to the limit as h approaches 0. Oops, forgot one thing here. How about we divide that by h? And then we need to simplify this. Well, what's x plus h squared? If you need to, off to the side, you can do x plus h times x plus h. That's x squared plus xh plus xh plus h squared, so that's x squared plus 2xh plus h squared minus x squared. And just like always, we look, can anything cancel? Okay, look, the x squareds cancel, but nothing else cancels. So now what? Well, there's still, we still can't do the direct substitution because we haven't canceled anything on top and bottom. So something has to cancel. Well, I notice that there's an h in common on the top, so if I factor that h out, if I gave you the problem 2xh plus h squared and I asked you what's in common, I think we could all agree that there's an h in common, and then we're able to factor that h out, and that's what I just did on this side. And what happens when I'm able to factor the h out? Now the h is canceled because it's a factor. So now that I've done that, we have the limit as h approaches 0 of 2x plus h. Well, now we can do our direct substitution. Plug the 0 in. We got 2x plus 0. So the derivative of x squared is equal to 2x. Now remember, the limit's gone because we've done our direct substitution to identify what it is at 0. So at the very end, we're not writing the limit anymore because we've done our direct substitution. The derivative is equal to 2x. So once again, there's another example of a quadratic. If we did x squared plus, let's say, 2x, you would do the same thing. You would just have a little bit more stuff on top, but the process is still the same. Alright, let's do one more today. We'll do, this is just a constant. And so, here we go. We have the limit as h approaches 0 of f of x plus h minus f of x all over h. And now this one might seem a little strange because, well, there's no h value, there's no x value to plug anything in. Well, it's just a constant. F of x equals 8 or equals 5 is just a horizontal line. So if I just plug in x plus h, no matter what I plug in, I'm always going to get a 5 back because it's just a horizontal line. So that leaves me with 5. If I plug x plus h in, my output is 5. If I plug, x in, my output is still 5. And so now you have the limit as h approaches 0 of 0 over h. Well, you can't do your direct substitution. You just need, think about this one. Well, as it approaches 0, what's going to happen? Well, you have 0 divided by really small numbers, but not 0, because it's as it approaches it, so it's not undefined. It gets closer and closer to that value of 0. So the derivative is equal to 0. So the limit as h approaches 0 gets closer and closer to 0. Once again, it's not 0 divided by 0, it's as it approaches 0, not what happens at 0. So would this be true for all constants? If f of x was equal to 2 or negative 10, would we always get a derivative of 0? Once again, you can kind of think through that process on your own and see what you come up with. So we got a couple more we're going to do, but not today. I'll do them on the next video. We'll do rational, and we'll do square root functions. So we've gone through, kind of just to do a quick recap, we've gone through what a secant line is so that we can help ourselves approach the slope of that tangent line, and what we found out is it was a limit. And so as we did that, we defined what a derivative was, the limit as h approaches 0 of f of x plus h minus f of x over h. And then we just did a couple examples. We did two linear, we did a quadratic, and then we did a constant. So those are the ones we're going to work on, and then we're kind of going to continue to build onto some more as we move on. Thank you.